So welcome here to the Learning Machine seminar today. Fredrik Carlsson of ri.se is going to talk about semantic sentence embeddings with contrastive tension, a work under submission. So I think, Fredrik, that you can start now.
All right, and as Olof said, my name is Fredrik Carlsson, and today we will be talking about sentence embeddings. And when we speak about embeddings, what I'll referring to is representing a concept as a point in some type of meaningful vector space. I believe most people are familiar with this, and using this method of representation, we can easily cluster things. It's easy to compare things, so we can quickly rank. And it also, of course, has the benefit that most, or if not all, of the current state-of-the-art machine learning models has inputs as continuous vectors. And just for an example, if we were to take, for example, sentences in, let's say, Reddit or something, and we were to try to rank them in comparing them through some sort of similarity measure, like if we take 10,000 of these sentences and we use the state-of-the-art method to pairwise compare them, it's going to take roughly 65 GPU hours with the top-notch GPU. However, if we first run like the sentences through an embedding method, so that we create an embedding for each separate sentence, and then we compare the embeddings, we can do this in about 5 seconds. So I mean, apparently it's very, very efficient to do this. And I mean, it's kind of mandatory. Like you can't keep comparing things pairwise. So embeddings are ubiquitous. I believe most people might be familiar with word embeddings, and there exists many common algorithms for this. We have word2vec, glove, fast text, etc. And usually what we see is that words that have similar semantic meaning will end up being close to each other. And that is exactly what we're out here for. So one could potentially find use cases of embeddings that are not inherently like semantic. Maybe we want to do something else, like determine if something is offensive or classify against some other sort of metric. But what we're interested in here is semantics. And once we have created the embeddings in some sort of algorithm, we have various metrics we could use to compare them against. I mean, we have the simple Euclidean distance, which is, it works fine. We have Manhattan distance, which is basically just an optimization. Like we don't have to do the square root to calculate this metric, but it works well. But what most people end up using is the cosine similarity. It is a bit more expensive to calculate, but it also has the added benefit that we get a metric that is clamped between -1 and 1. So moving on to semantics. Semantics is itself a somewhat tricky concept, I suppose, but disregarding all the philosophy that is behind what is semantics and what is not semantics, we try to stay pragmatic, and we say like, okay, let's have a bunch of people rate how semantically similar things are without ever having to define what semantics is. So for example, boy and man would have a human rated similarity of 4.2, where 5 is the maximum similarity and 0 is like no similarity whatsoever. And we do this for a lot of word pairs, and then we start comparing how well this like correlates with our embedding space. And we usually measure this correlation in Pearson, but also in Spearman correlation. And for you that are familiar with Pearson, but not Spearman, what you need to know only is that Spearman is only the Pearson correlation applied to the rankings. So if we have, for example, the cosine similarities here, we would rank them and say that yes, boy, man, rank number 1, apple, orange, rank number 2. Then we find that man and sleeping as number 3, and so on. And we take the Pearson correlation of the rankings. Now, to sentences. So it's kind of the same thing here, right? We try to represent each sentence as a point in this vector space. And we do the exact same thing. We ask people to give a human sentiment similarity, like, okay, a woman is sleeping is somewhat similar to the girl is napping. So people would tend to rate that high. And we'll have sentences like, I'm learning the piano, a woman is sleeping. They don't really have any semantic similarity going on. And there exists roughly 12,000 or 11.5 labeled sentence pairs. So there isn't like an overflow of data here. We're kind of working in a somewhat sparse data environment here. And I mean, it is very easy to find non-semantically similar sentences, right? If you were to just sample 2 sentences from a book, a data source, what kind of corpus, they will probably be very non-semantically similar. So finding these like edge cases of 2.5, 3, 4 are far more trickier to collect than like 5 or 0. And perhaps the most straightforward approach to creating sentence embeddings is using the already well-established word embeddings and simply taking an average. So if we already have an embedding space of words, we can create a sentence embedding by simply taking the average or the mean word embedding. And once we have done these for 2 sentences, we can then compare these, and we have created a sentence embedding method, right? This turns out to work somewhat fine. So the 12,000 data points that has been collected through the years 2012, 13, 14, 15, 16. So the data is separated into 5 different sets or tasks, what you call it. And we can see that Word2Vec performs slightly better, or somewhat significantly better than Glove in this case. However, of course, there are more sophisticated methods. And kind of the first method to be popped out there was skip thoughts. And it was proposed in 2015. So this is pre-transformer NLP style. And they utilize an encoder-decoder structure where they try to predict nearby sentences. So the encoder and the decoder both consists of LSTMs, where we take the first word, we put it through, then we take the second word, we put it in, and so on until the whole sentence is in. And what comes out of the encoder is what we call the sentence representation. We then take this sentence representation and we run it through the decoder. And what they do here is they're going to try to predict not only the next sentence, but also the previous sentence. And what they did was they really increased the embedding size. So all these other algorithms of the word embeddings, like Word2Vec, Glove, you usually see them in a ballpark of 300 dimensions of that kind. Could be less, could be slightly more. But Skip Thoughts went ahead and you know what? Let's do 4,800. Why not, right? And as I said, they're trying to create a sentence embedding that when run through a decoder, it will be able to predict the previous sentence and the next sentence. So an example of this would be, let's say we have the text, this is the first sentence, followed by this sequence of words, and finally we end this paragraph. We would then encode the followed by this sequence of words. We run it through the LSTM encoder. We generate a sentence representation. And now we run this sentence representation through the 2 separate decoders. And we ask them to predict either this is the first sentence or finally we end this paragraph. And unfortunately, this does not work as well with semantics as one would hope. It does fairly fine on different sentence tasks, but when we're out for semantics, skip thoughts actually perform worse than simple averaging of both glove and word-to-vec embeddings. And this is kind of unfortunate if one takes into consideration that skip thoughts was trained for 2 weeks, which at the time of 2015 was like a huge training time. However, in 2017, we had the introduction of inference. And inference basically bases its algorithm on the idea that instead of trying to predict like next sentence, previous sentence, or anything like that, it says like sentences should be based on a natural language inference task. And it's common in NLP to formulate a natural language inference task as a classification problem. So you pass 2 sentences to the model, and we try to ask the model whether the relationship between these 2 sentences are either an entailment, a neutral, or a contradiction, right? So if I were to give you first a sentence, a man is reading a book, and then I say the man is sleeping, then the answer would be that no, this is a contradiction. You cannot read a book while you're sleeping. And 2 men are laughing. 2 men are laughing at a joke. It's neutral. It could be that they're laughing at a joke. They could be laughing at something else, right? But if I say a soccer game with multiple males, it entails that some men are playing sport. And this has the downside that requires labeled data. So while skip thoughts was completely self-supervised, we could just throw in a large corpus of data and take the next and previous sentences. Here we actually require labels for the training algorithm. Luckily, there exists approximately 1 million of these labeled training samples, so it's definitely more than the 12,000 semantic similarity samples that we have. The architecture of inference is a Siamese network. So we pass both the sentences to the same model. We create a sentence representation of that. And then we concatenate and combine these 2, and we run them through a simple classifier. And in this case, inference is also based on the LSTM encoder. And as an example again, here we would want to classify a contradiction. We then run a backprop through the classifier, through the sentence representations, and through the encoder, with the intuition that sentence representations that are good for the, like, how should we explain that? So I suppose the intuition here is that once you have a representation that is good for inference, it will be good for other tasks as well. Like a lot of these things don't really have clear-cut, at least not to me, like why this would be good for semantics, it's not super obvious to me. But anyhow, moving on. It does, however, disregarding my non-intuition here, it does work, right? It outperforms at least word-to-vec and the previous methods, and it was definitely the state of the art of semantic sentence representations at the time. And then, of course, everything changed. So in late 2017 and up until now, we have been bombarded with different transformer architectures. And for those of you who are not familiar with transformers, they are in essence huge, often very large language models, pre-trained on only, modeling the distribution of language. And currently, near every NLP task is being beaten by transformers. And there's multiple different architectures out there: BERT, Roberta, Electra, GPT, XLNet, and so on. And the whole idea of most of these is basically the idea of self-attention. I'm not going to explain this here, but in essence, it's that we pass all the words at the same time in parallel through the model, and we allow the words to attend to each other. So unlike the LSTM encoder we saw, where we put them into a sequence, we put them all in parallel, and we let them put attention to each other. This makes for very good computation. So it's very efficient. So although these models are vast in the number of parameters, it's somewhat more trivial to train them than the LSTM-based encoder decoders. And like there does exist a lot of variations in these models, like Roberta, BERT, XLNet, GPT, and so on. But a very common thing that people do is what's known as masked language modeling. So here we have a sentence, I'm a fan of ML. We're then going to go ahead and mask some of these words. And then we're going to pass them through the model. And in the end, we're going to ask to classify which word was masked here. So we want the model to have a good understanding of language. So when it gets the a fan of ML, it's going to try to predict am and off. And yeah, this is basically done on a lot of data, right? I mean, there is a lot of text data on the internet. There exists these terabytes of corpuses out there, corpora. And yeah, the models are in general very large. You can get the smallest models perhaps have like 66 million parameters, and the larger models have like, I don't know, 1.5 billion parameters by now, or probably more by now. And they do work for a lot of modeling tasks, right? But now the question is like, how do we extract sentence representations from this? And what happens as we pass all of the words in parallel through the model is that the model will keep a word representations for every word throughout the model. So it's going to pass layer by layer. It will keep a word representation. And this embedding or word representation usually has a dimensionality of 768 or 1024 or something that is computationally efficient. But we want a sentence representation. And the easiest thing, of course, is just to take an average of this. And you will see that this is commonly how people extract. You can do it in other ways as well. I mean, you could extract maybe a sentence representation in the end or the start or the intermediate layers. And you could potentially like make weird combinations of this. Maybe you want to take like the penultimate layer, the first layer, and the layer 12. You mean that. But in most of the cases, what people do is that they take the final contextualized word embeddings, take an average over that, and we get a fixed size sentence representation. However, if we just analyze the actual sentence representations that we get throughout the layers, we see that they do not perform as well. So what we've done here is that we've taken 5 of the most common transformer models, and we extract sentence representations per layer. So we would take one sentence representation for layer 1, layer 2, layer blah, 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 until the end. And then we do the semantic evaluation of these representations. And unfortunately, we find that they perform very subpar compared to the other methods. So although these methods have been trained on vast amounts of data, it does not seem that the pre-training task yields good semantic sentence representation. which is unfortunate, of course, since there has been a lot of resources spent on training these models. And something that was proposed in 2019 was that can't we just fine-tune these transformer models with the inference training objective? So we take the exact same thing, we ask them to predict the relationship between two sentences and say, is it an entailment, contradiction, or neutral? And the only difference here is that we're going to use the transformer as an encoder instead of the LSTM encoder. And surprise, surprise, this works really, really well. So we can see that by simply first pre-training a language model and then doing the inference objective, we kind of drastically outperform all of the previous methods. And I mean, this is well aligned with current intuitions of NLP and I suppose deep learning in general, that you do gain a lot by simply pre-training and building good cohesive representations in general, and then fine-tuning towards a task. So in essence, the biggest difference between inference and S-BERT is that inference uses an LSTM and trains directly on the 1 million natural language inference pairs, while S-BERT first pre-trains on a lot of text and then fine-tunes with the inference. And just comparing them side by side, we see that the fine-tuning has mostly affected the later layers of the model, which is to be expected. We see very little change in the earlier layers and the middle layers. And of course, since we are applying the training objective to the final layers of the model, this is somewhat to be expected. And now we finally get to our method here. So we have developed contrastive tension. It's me, Amaru, Evie, Erik, and Magnus. And what we find is that we outperform all of the previous methods. I will explain the method in a minute, with the big benefit that our method does not require any label data whatsoever. And yes, from here on, I hope it will stay somewhat transparent what we're doing. And an observation that we made with these transformer models was that, okay, fine, we know that the representations in either the final layer or the intermediate or the early layers are that performative when it comes to semantic similarity. So we started looking into how are these embeddings positioned in the embedding space. And what we found that near all of the embeddings show a very high cosine similarity. So what we have to the left here is that on the x-axis, we have these different human rated similarity scores. So a sentence pair that has an super high similarity score is going to be to the right. So for example, an identical sentence pair like I like apples, I like apples. Most people would rate that a 5 out of 5. And a sentence pair which is like I like apples, yesterday I went swimming, would have a very low similarity and be to the left. However, when we run these through the unfine-tuned BERT model, we find that all of these embeddings have a somewhat high cosine similarity. And what this implies is that more or less all of these embeddings end up in a very narrow span of the potential embedding space. So in theory, we could have one embedding being 1 and one being all the way to -1. However, we find that nothing ever goes below 0.7 here. So the span of this, what you call native or unfine-tuned embedding space, is narrow. And we thought that, wait, maybe this is not as it should be. So we had the idea that we mainly want to dissipate this. So we, of course, want to keep a high similarity for semantically similar sentences, but we would rather see that this one goes down. And it's important to distinguish that this does not necessarily have to go all the way down to 0 or -1, since all we're measuring here is correlation. So you could, in theory, have a straight line from 0.8 to 1, and it would get a maximum score. But we see clearly now that there's a lot of overlap here. So we have the mean here, and this is the maximum and the minimum value. So we can see that although there is a trend of it going upwards, it's not super clear. So to the method. What we do here is somewhat different from previous methods in the sense that we're training 2 encoder models at the same time. And then we're taking the dot product of these 2 models and we're saying, okay, we want to maximize the identical sentences and minimize the correlation of the differing sentences. And at a first glance, this does not seem very intuitive. And unfortunately, the more you look at it, I'm not sure how much more intuitive it's going to get, but we'll try it. So what I'm saying here is that we have 2 different embedding spaces, and we're going to initialize them identically, meaning that in the start, before we do any training, we will have 2 embedding spaces that have completely identical positioning of all potential sentences, right? And then we're going to say that, okay, I want the sentence embedding between these 2 models. If they are the exact same sentence, we want to maximize the dot product, meaning that we want to pull them together and potentially increase the magnitude of it. However, if I give 2 different sentences, like I like apples and I went swimming yesterday, we want the 2 models to disagree on a sentence embedding. And the reason we can't just use 1 model for this task would be that if we were to have the same encoder, like the embedding for the same sentence would always be the same. I mean, of course, if you have transformer 1 and transformer 1 and you pass in S of A and S of B and they're the same sentence, you will end up with the same sentence embedding here. And the difference would be that if we have 2 different models, so let's pretend that this is the embedding space of the first encoder, this is the embedding space of the second encoder, then as we pass them 2 different sentences, they're going to be incentivized to like dissipate or move away from each other to try to minimize the dot product. And if we pass them identical sentences, they're going to try to pull together on that representation. So they're going to try to agree on a representation for identical sentences, and they're going to come up with a disagreement of different sentences. And I suppose you could try to imagine this as the 2 embedding spaces trying, like if we put them on top of each other, they're trying to like find a matching where they have identical sentence representations for identical sentences, but that they also have dissipated these sentences for differing sentences. Now, if we run this through the example of only having 1 encoder, we see that if we were to pass the same sentence, we would only maximize, like the model would only be incentivized to increase the magnitude of that vector representation. So we would quickly lead to a complete overblow of the embedding space. And yeah, the whole thing just collapses somewhat quickly. Please let me know if there's any question. I'm just gonna ramble on until either somebody stops me or I run out of slides or time. Is there any questions so far?
So, Fredrik, we have some questions in the chat.
Yeah, I was asking probably the most of them, but I think it makes sense to now move them to the end because they don't fit in right now.
Okay.
Should I wait?
So go on. And
all right, I'll continue then. So yeah, please just interrupt me. I don't have the chat open right now, so just either all of you can scream or somebody could just let me know.
Yes. Well,
yes.
Otherwise we'll keep the questions afterwards.
Awesome. All right. So this is the intuition behind the algorithm. Now, of course, this would work with different sentences. The problem is that if we only keep one transformer and we say like, okay, different sentences should be different, what happens after a while is that we completely deteriorate the embedding space or the knowledge. I mean, what kind of works here, or at least I'll be honest, this is only our intuition of why it works. It's because that we think that when we have two identical sentences but two embedding space, we kind of incentivize the model, to not go too far away from where it was before. So we're thinking of this as a tension between remaining in our previous embedding position while dissipating different sentences. We have tried like only fixing one of the transformers to work as an anchor, but that did not end up working as well at all. Can't even remember if it actually completely crashed or not. But the intuition here is that we try to have a tension between dissipating different sentences, embeddings, while retaining or agreeing upon identical sentences. Yes, and as I said, like we require no labeled data to do this. We just need a bunch of sentences. They don't even have to be cohesive in any way or subsequent. And for all of our experiments, we just simply took English Wikipedia and sampled random sentences, completely uniform. And what we find that when we apply contrastive tension to BERT, we see that indeed we have managed to decrease the similarity for differing sentences. And we also see that sentences that have been humanly rated to be semantically similar, they have remained like close in the embedding space. So what we kind of assume has happened here is that we have in fact dissipated the embedding space somewhat without removing too much of the like pre-trained knowledge that we gain throughout the pre-training task.
Now one of my questions fits well. Do you have a plot with this one as well, where you have the sentence BERT cosine similarity plotted?
For the sentence BERT?
Yeah. Right now you have BERT base, right?
I do, and I think it's going to be showing up.
Well, if it's later, then we don't have to go now.
I think it's going to show up. I hope so. Otherwise, I have it in the paper, so I'll try to show it some way.
Cool. Thanks.
I can just spoil it, and I think it goes like between 0.3 and something. So it seems to dissipate the embedding space even more, but it also has a higher deviance. All right, moving on. So we can see that as we apply CT, we see like a similar end result as we would expect with like S-BERT and all that. We see that it's mainly the latter layers of the model that are affected by this. And I suppose it's more obvious when you look at like the XLNet base, which performs completely horrible before we apply this. And we see that as training goes along, the latter layers do show more and more semantic cohesiveness. And yeah, I suppose this is somewhat intuitive if you just buy into the whole idea that CT works. And I guess I should also mention that since we do have two different models in CT, what we do is that we evaluate both of them and then we throw away the best one to make it like a worst case scenario. So the results we see, or we saw here, are the worst case scenario. So we have trained 2 models, and then we evaluate both of them, and we throw away the best one to say, like, okay, this is the worst we're gonna potentially end up with. And they differ very little in the score. As I recall, don't quote me on this, I would say that the best model perhaps performed like 1 point better on average. So maybe this should be like 76 if it's the best case. But there's not a huge difference between the two. And for the most part, there's also not a very big difference between different runs. So if you run the algorithm 10 times, we're going to have a somewhat small standard deviation between the scores. Moving on to more results before we hopefully have time
Quick
for
question.
Yes.
So you had 2 transformers, but I guess it's 2 BERT that you have, BERT large, right?
We have tried a bunch. The ones we're going to report mainly are BERT large and BERT base. But we have tried
it's not a full encoder-decoder transformer thing. It's basically the encoder only, right?
Yes, we have also tried this on encoder decoders like T5, and it works. It does not show as good results as only doing it on encoders.
And what's the difference between the BERT1 and BERT2 encoders then? Is it simply that it's initialized the same way, I think it says here, but it's simply trained differently in some way? Or what's the difference between the 2 different BERT models?
Right, so they are, in a sense, like they are identical, but they don't have shared weights, meaning that they are allowed to differ throughout the training. And they will differ since they will be passed different sentences. So the first transformer model might be passed the sentence, I like apples, while I went swimming yesterday is going to be passed to the second. So right after like the first training example where they're given different sentences, they will start to differentiate their embedding spaces.
Okay, so it's only the random selection of sentences that makes the difference between them two, right?
Correct, yes.
Okay, cool, thanks.
I mean, yes, any more questions?
Yep. Do you think if you had like if you put in both versions of combining the sentence to the model, so you had sentence A to transformer A and sentence B to transformer B, and then you try to get them to get different representations. If you then switched it up and did a second round where you switch the where you put sentence B to transformer 1, sentence A to transformer 2, and then do the same backprop step, that would probably end you up in a similar place to where you would have been using just one model to begin with. Or would you disagree with that?
I would probably disagree with that intuition, yes.
Okay.
So my understanding would be that, okay, do I pose the question correctly if I say that, okay, first we have sentence A and sentence B, we pass them to 1 and 2, and then we switch the order of sentence A and B and we pass them.
Yes.
So my understanding would be that since after the first backprop step, they will be different. So when you will like permutate the order of the same sentences and pass them again, since the models are different, like the gradients will be different. So I don't necessarily think that they will go back to the same step. I mean, the objective is still, to push away. And if they've already started to push away in a certain direction, the gradient will be pushing towards, still pushing those away. So I don't think that, that once we push them away, they're gonna next time try to collapse again. I don't think that would happen.
Yeah, but you didn't try this switching between them to have a sort of like a balanced approach to this, I guess.
No, that is true.
Yeah. Just curious, and I think it maybe if this works, then maybe it's better to do without the balanced approach. But yeah, thanks.
It's an interesting question. It's worth of pursuing, I suppose. Where were we? We looked at this, right? And so yeah, basically here is just a bunch of results from the whole study. So We have the old work of like inference and something I did not speak about, which is the universal sentence encoder. And then we have the regular BERT models in all three sizes. So BERT large, I think, has around 340 million parameters. BERT base, I'm gonna say 120, and 66 million for BERT distill. And we do see like BERT models right off the bat perform worse the bigger they get. And we see that BERT large, for example, has 53 and 51 on Spearman and Pearson, but BERT distill performs a lot better. And we'll get to this, why we think this is the case. But we also see that, okay, S-BERT clearly outperforms the regular BERT models. And S-BERT VK is kind of this hack where instead of saying, okay, I only want to look at the final representations of the transformer and then average over it, they do like a weighted averaging of all of the word representations throughout the model. However, we also, to our pleasant surprise, see that BERT does perform, no, CT outperforms all previous methods. We see that just applying CT to BERT large gives 75. And what is also very interesting is that when we apply CT to BERT distill, which is 88% smaller than S-BERT large, we do in fact outperform that, which is very nice. Now we have a very small model, which still gets at least previous state-of-the-art results. We do, however, also see a slight increase in performance when we do CT to a model that has already been trained toward the inference training objective. So if we were to take these BERT models and we first fine-tune them with the S-BERT objective, and then we apply CT, we see like a minor improvement again. So it for sure shows that like the initialization of the model prior to the CT is of very big importance here. And one of the upsides with CT, since it requires no labeled data, is that it's easily applicable to any language, as long as we have a pre-trained language model and available text data. So what we did was that we took a bunch of BERT models that have been specifically trained on different languages like Arabic, English, Russian, Spanish, and Swedish, and then we just applied CT to that. We also tried this with a model that has been trained on multiple languages at once. So it's been trained to, I think it's 100 languages or 1,000 languages. And we do see that CT does improve performance for all of these models in all of these languages, which is indeed pretty neat. Moving on, the final thing we kind of did for the CT was that we tried a bunch of different corpora and see like, do they yield different results? And we did find that Wikipedia worked the best out of the three that we tried. And the difference between these three corpora is that Wikipedia, you all know. Books, I think, is like 1,000 books or something or more. It's a large book corpora of random books, I suppose. And then we finally have random, which is somewhat interesting because random is only us taking like random words from the vocabulary of that language and putting them into a sequence and then running them through a model. And we do actually see that like both BERT distill and BERT base get better without having any textual training data at all. So potentially we could just run noise through the model and do the CT objective. And it at least yields like a tiny improvement. However, we do see that when we try this on the BERT large model, it completely deteriorated. It destroyed any sort of semantic performance. So I would not recommend it. I think it's an interesting finding, but probably not the way to go forward. Is there any questions about CT? Because either we have a discussion now, which might be of need, since I don't think this is like one of the algorithms where it's like, I see why this works. Or we talk about how we also improved on the like supervised sentence representations. So is there any questions?
Yeah, I have another one. You reported a number of results here, the results figures. Those tasks that you had, those were the semantic similarity of sentences task, or were these other
Yes.
tasks? And
These are
have you
all semantic similarity tasks.
And have you tried to see if this method of fine-tuning BERT yields improvements for other completely unrelated tasks that you do with BERT?
We have, and we don't see any major improvements at all in near any of our tasks. And I suppose that is, I'm not sure if that is intuitive or not, but and here's also the thing, like if you compare against all of these methods, we have like BERT, S-BERT, S-BERT VK, BERT large, and whatnot. I mean, the tasks that you evaluate sentences on that are not semantic is somewhat like, because you usually apply like a linear classifier to the embeddings and say like, what is the sentiment of this sentence, or is this an entailment or not? And you kind of find that BERT, like just the regular BERT, performs very good on this. Just taking sentence representation of BERT and then trying to do like not semantic but sentiment classification or entailment, they perform better than both S-BERT and BERT CT. I think that the one that performs the best are the universal sentence encoder in this case. So to answer your question, no, we don't see any improvements on other than semantic tasks.
All right, thanks.
Any other questions?
Yeah, quick question. Of course, really impressive results and cool work. So congrats on that. Did you ever have time to also compare with the Facebook laser embeddings? They have, their own like language agnostic sentence embeddings in laser.
It does not seem that laser performs well at semantics, which is basically what we're doing here. I think I've heard that laser is supposedly good on tasks, but I have not investigated. No, they're not usually mentioned in the literature of semantic representations, from what I've seen at least. I might be wrong.
Yeah. Some similarity tasks seems to perform really well actually, so it would have been nice to have some comparison. But okay, thanks.
Yeah. Any other question? Well, if not, then I'll guess I'll do like a 5-minute quick round of hacking the supervised scores as well. So what we're doing here is that we've been mainly like saying, okay, we're going to train on something completely uncorrelated, and then we're going to compare the results on semantics. There is also this thing where people actually fine-tune on the little semantic data that we have. And there is this test set or data set called STSB, which is basically a collection of the 5 years of STS data. And it's done some filtering, and they've split it up into 5.7 thousand samples of training. And we have some validation and we have some tests. And what S-BERT does here is that they say, okay, let's just directly try to tune the actual cosine similarity towards what people has been like labeling things. And this works really well. So what they do is that they say, okay, we know that the human labels are in the range of 0 to 5. And we're then going to say that, okay, between 0 and 1, we're going to linearly label these. So we want the end curve to look like this. And indeed, if they were to achieve this, they would get a perfect correlation score. And this performs kind of well. What we say, however, is that, no, wait, why 0 and 1? I mean, the 0 is completely arbitrary. All we need is a line in some sense, and we should be good. So we say that, you know what, let's try to do something that is less destructive. Let's say that, okay, instead of going all the way here and trying to move this embedding space a lot, we say just move it enough so that you actually get a good correlation score here. And we do find that this improves for all models. So here to the left, we see that before we do any training on the specific STS data, and we do see that, applying CT to an S-BERT model gives the best score. However, if you only take S-BERT or BERT, and then you start doing the actual regression task, which I mentioned here, then we find that it improves into the state where it outperforms all of the uncorrelated or unsupervised methods, right? However, we also see that when we do our relative regression labels, we improve the performance of this. So yet again, we find at least that there is a clear improvement of, I don't know, 1.37 or something. And I suppose the final thing that you should mention is that if you do this on other models that are not BERT, maybe Roberta and XLNet, and instead of only looking at the bottom here, and you try to label it between this, and you instead do a hyperparameter search between 1 and 0, then you can beat previous state of the art by a large fraction. So this is not yet published results. This is for the next paper, which we're currently writing, but you can really beat state of the art in the supervised results quite significantly if you just start taking into consideration these arbitrary regression labels. And yes, I think that is all I have, and I will be happy to try to answer any questions.
Quickly to that last one you're saying, so that's pairwise regression.
Indeed, yes. So
for the Roberta, the very last one you mentioned.
Yes, it is.
Okay. Thanks.
No problem.
Do we have more questions for Fredrik?
Yes, I would like to ask. There are other what they call inference tasks. Have you looked at? I mean, the tasks you're looking at here. It's similarity between sentences, right? If they natural contraction attainment. It's a quite special kind of challenge. There are also similar challenges that are to try to understand the capability of various techniques. Have you looked at anything else, or why just this one?
And do you mean why we only evaluate towards semantic similarity, or?
Yeah, just STS.
Mm-hmm. We have looked at other things. We don't see an improvement in other areas. What I tried to allude to earlier was that we basically don't see an improvement between, S-BERT, of course, is going to be better at natural language inference since it had been specifically trained towards that. But S-BERT does not differ drastically from simple BERT, and CT does not improve anything except semantics, which improves a lot. So we have tried. We do not find any improvements in other areas, unfortunately.
Okay, thank you.
One more question here as well. It's actually a follow-up from what Philip asked, but if you think about more supervised tasks, something else than paired could be to have a ranked similarity task, saying basically, I have a set of sentences. I want to predict which is most similar, and then I want to have the proper ranking of these sentences and see how that performs. There is little research in this field, but it's something that we at least at Paltarian has been trying to look into a bit more because it's a very high practical use. I'm not sure if I make sense in explaining this, but do you know what I mean? And have you looked into any of these kind of ranked similarity?
So what you would say, I mean, how does this differ from the Spearman correlation? Are you saying that you want to have a similarity measure between all possible combinations of sentences, or is it only that you want to rank them in pairs, how similar they are?
Sorry, I got a call in the middle, so I missed your first words there. But I heard the last part, which was something if you want some kind of Spearman correlation or something. But no, it's not the Spearman correlation I'm after. In this case, it's basically given that you have a list of ranked sentences and you want to train a model to be able to do that, then you have these kind of traditional, ranking metrics, which can be top 1 or NCG and these kind of, or top 5 or something scores, which is rather different, I would say, than just having like a regression similarity score or classification task. So that is basically my question. If you have tried to look more into this kind of ranking objectives with the metrics that they use.
Right.
This works.
I think I understand. I mean, I have done that for like image retrieval, right? You get a lot of images and you got a lot of text captions and you try to like rank them in how. So I have looked at that in that context. And as you said, like I have not seen a lot of that in NLP, like purely textual. I've seen it cross multimodal, but I have not seen a lot of text retrieval ranking tasks. So I don't know, I have not looked into it yet. But there's definitely, as you say, I can see a lot of practical utilization of that, right?
Yeah, exactly. Some surprising results. We have some initial experiments from Tatorian as well, which is a bit concerning because TF-IDF works surprisingly well here, even compared to S-BERT, which is annoying. Yeah, that's another story.
I think we have had similar results. I mean, the classical models or methods seem to be working fairly well in certain tasks. I mean, you should never underestimate the old schools, I suppose.
Yeah, exactly.
Anyone else?
If no one else, just one more question from me as well. And this is more for the multilingual aspects of the work. I think you mentioned that you had at least the multilingual vanilla BERT in there, but you haven't tried anything with like XLMR or something like that, right?
Yes, we have. And I decided not to include XLMR because I thought it was too much. But in the paper, we have an extra row for XLMR, and it also improves the result for XLMR on every language.
Awesome. Cool. Thanks.
So if there are no more questions, then let's thank the speaker. And next week, there'll be a break. No seminar on the 29th. But in 2 weeks' time, there will be another talk. Welcome back then. Thank you, Fredrik.
And thank you all for listening.
Thank you.
Bye.